In this lesson, we'll be going over electronegativity and polarity. Using electronegativity and a couple of other rules, we can determine the polarity of any molecular compound. Jumping right into it, what is electronegativity? Well, just like the atomic mass, the ionic charge, and the atomic number, electronegativity is one of the numbers next to the elements on the periodic table. Electronegativity is an atom's ability to attract bonding electrons. The strength of electronegativity increases from about 0.7 to 4.0, with francium having the lowest electronegativity and fluorine having the highest at 4. This makes total sense because metals like francium, potassium, calcium, or aluminum do not attract bonding electrons, but rather give them away to nonmetals in ionic compounds, like nitrogen, oxygen, and fluorine, which have higher electronegativities, suggesting that they have a stronger attraction for bonding electrons. Now, how can we use these electronegativities to our advantage? Well, based on the difference between the electronegativities, for example, the difference being 3.3 between francium and fluorine, we can interpret this number to figure a certain characteristic about the compound. If the difference of electronegativity is 1.7 or greater, this means that the compound is ionic. Let's take calcium chloride for example, CaCl2. We know that this is an ionic compound because there's calcium, the metal, and 2 chlorines, the nonmetals. But we can confirm that this compound is ionic by finding the difference of electronegativity. On my periodic table, the electronegativity of chlorine is 3.2 and calcium is 1.0. The difference between the two electronegativities is 2.2, further proving that this is an ionic compound. What's interesting about this is that two nonmetals can have an electronegativity difference of 1.7 or greater, and they can actually become ionic compounds, even though no metals are involved. Anyways, moving on. What if the electronegativity difference is 0? How can this happen? Well, on the periodic table, some elements actually have the same electronegativity, meaning that there's no difference between the strength to attract bonding electrons. Let's take nitrogen and bromine for example. They both have an electronegativity of 3.0 on my periodic table. But of course, we can also get a difference of 0 between two electronegativities by making a molecule of 2 or more of the same atom. Let's take an oxygen molecule for example, O2. This is what the Lewis structure would look like, and both have the same electronegativity of 3.4, meaning that the electrons are shared equally amongst both atoms. We call these bonds nonpolar covalent bonds. But what if the electronegativity difference is greater than 0 but less than 1.7? Let's take a look at hydrogen chloride. Chlorine has an electronegativity of 3.2, while hydrogen has an electronegativity of 2.2, making their electronegativity difference 1, which is in between 0 and 1.7. Like we said before, if the electronegativity difference is 1.7 or greater, then that means that the nonmetal had a strong enough electronegativity to fully take the electron away from the metal. And if the difference was 0, then the electrons would be shared equally. But if a number is between 0 and 1.7, these electrons are shared unequally, causing there to be localized positive and negative charges. Let's take a look at the hydrogen chloride Lewis structure. Taking a look at both electronegativities, chlorine actually has the stronger one at 3.2, meaning that it has a stronger attraction for electrons. If this is the case, and more negative electrons are around the chlorine and less around the hydrogen, then there should be a localized negative charge around the chlorine and a localized positive charge around the hydrogen, causing there to be two poles in this molecule. Hence why we call this type of bond a polar covalent bond. Next to the atom with the corresponding localized charge, the symbol is in between a figure 8 and an S, along with its charge. So chlorine has a negative and hydrogen has a positive. Keep in mind that the greater that this difference of electronegativity gets, the closer it gets to being like an ionic compound in which the electron is fully transferred from one atom to another. meaning that if we had a molecule with an electronegativity difference of 1.6, its localized positive and negative charges would be much stronger than this hydrogen chloride, as there is a larger discrepancy in where the electrons are attracted to most, making the negative pole a lot stronger, which in turn also makes its positive pole stronger. Moving on, we can forget about ionic compounds and only focus on polar and nonpolar. As for most molecular compounds, it's difficult to read if the compound is polar or nonpolar simply by just calculating electronegativity differences. Let's take carbon tetrafluoride for example. Drawing its Lewis structure, it looks like this, with carbon in the middle surrounded by 4 different fluorine atoms, each connected to the carbon with one bond. After drawing all the electrons, let's take a look at the electronegativity difference. Since fluorine has an electronegativity of 4.0, and we are subtracting carbon's electronegativity of 2.6, the difference is 1.4, meaning that this molecule only has polar covalent bonds. But does this mean that the molecule is polar? Well, let's take a look at the structure of the molecule. Surrounding the carbon, there is one on its left and one on its right, as well as on top and below it. Similar to how we discussed how non-polar molecules are formed, in which the electronegativity difference is 0 and the electrons are shared equally, the same can be applied to this, seeing as the electron attraction for the fluorine on the left counteracts the electron attraction for the fluorine on the right, the same being true for the above and below fluorine atoms. And if there's an equal attraction for electrons on all sides, then that would mean that there is no discrepancy in the sharing of electrons, meaning that there is no charge, meaning that this molecule is nonpolar. An easier way to figure this out is we can look at the symmetry of the molecule. It takes the same idea as looking at the electronegativities on either side, making sure everything's equal. And because this molecule is symmetrical both vertically and horizontally, that is further proof that this is a nonpolar molecule. What if we had a molecule like chloroform, CHCl3? Well, similar to the last compound, the C is in the middle, and then we have 3 chlorines that we can put around the carbon, and then finally place this hydrogen on this last spot. We can find the electronegativity differences for each of the bonds. And once again, they are all polar, seeing as they are between 0 and 1.7. Next, let's take a look at the symmetry. And right off the bat, we can see that going down the vertical, it is not symmetrical, seeing as there is a hydrogen on the left and a chlorine on the right. However, there is still a chlorine on the top and a chlorine on the bottom. Here, the electron sharing is actually equal, seeing as the same atom always has the same electronegativity, meaning that the electrons are shared equally, but not between these two. You see, chlorine has a higher electronegativity of 3.2, while hydrogen only has an electronegativity of 2.2. With chlorine being higher, this atom has a stronger electron attraction, and therefore has the localized negative charge, while the hydrogen has the localized positive charge, making this molecule polar. Now, we can use these tricks with the electronegativity, trying to find if there are polar or nonpolar covalent bonds, as well as the symmetry of molecules to find the polarity. There are some exceptions in which some molecules must be drawn differently. Like one of these exceptions being that when nitrogen is bonded with 3 atoms of the same element, like NH3 or NF3, this molecule will always be polar. So drawing out NH3 in a Lewis structure, we would know that the hydrogens would have the localized positive charge, seeing as they have a 2.2 electronegativity while nitrogen has 3. And we need to draw it like this, with these hydrogens out of the way of the nitrogen so that it can have its localized negative charge. Another one of these exceptions is when oxygen is bonded with 2 atoms of the same element. For example, H2O, water, will always be polar. You see, a good chemistry student would draw a water molecule like this, with hydrogen on either side of this oxygen. And this looks good, seeing as the molecule is balanced, and not knowing that this molecule is supposed to be polar, this wouldn't bat an eye. However, when we use the symmetry rule, seeing that there is hydrogen on either sides, then that would mean that there is an equal sharing of electrons. In this molecule, oxygen actually has the stronger attraction for electrons. And so here, the charge would be equal, but it would be an equal electron repulsion instead of an equal electron attraction. But anyways, to make this molecule polar, instead of drawing this hydrogen to the oxygen's right, we will draw it below the oxygen. That way, the molecule loses any of its symmetry. Also giving the oxygen the localized negative charge, seeing as it has the higher electronegativity, and the hydrogens will have the positive localized charge, seeing as they have lower electronegativities. Now, this isn't just for nitrogen and oxygen. The same rules can apply to other elements in the same chemical families as nitrogen and oxygen. For example, phosphorus, which is in the same chemical family as nitrogen, will always be polar if it is bonded with 3 other atoms of the same element. And same with sulfur, as it is in the same chemical family or group as oxygen, and when bonded with 2 atoms of the same element, it will also be polar. So keeping all of these rules in mind, you should have a good understanding of how to determine the polarity of molecules. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.